Okay, so today's lecture is going to be about evaluating classifiers. So we'll continue with looking at the classification and how we can evaluate the classifiers we learned how to work with last week, and then we move to clustering. So we start with a recap of last week's lecture, and then introduce how we can evaluate classifiers and move to clustering later on. So last week we introduced the concepts of supervised and unsupervised learning, where we had classification as an instance of supervised learning, meaning that we have a set of training examples which we can use to learn how to predict or classify new unseen examples. And we did that within the sort of the realm of vector space models, so things that we have already learned about, and we improved our understanding of vector space models in order to represent classes of objects rather than just individual objects or data points. And we briefly discussed also two main ways of or approaches to represent classes. So there was exemplar-based class representation, and an example of that was KNN, where each member of the class is a potential representative of the class itself. So there is no abstraction. We don't compute anything new. And the other one was centroid-based, or what we used in where we compute an average vector of all the members of the classes of the class itself, sorry, and that would be our centroid or our prototypical representative of the class. And then we also introduced different types of memberships. So an object could be or a membership function could be hard or soft, crisp or soft, and hard membership, it's an either or situation. So an object is either a member of a class or not. In soft membership, we had this scaled or graded concept of membership. So an object is a member of class A with a 0.4 probability, and a member of class B with 0.6 probability. And also fuzzy membership, where an object could belong to two classes at the same time. And these are sort of these type of memberships will also be relevant to clustering as well. And yes, and then we talked about Rocchio classification or Rocchio classifiers, so where we rely on centroid-based representations. And the idea was that for each class we compute a centroid, and then when we want to classify a new unseen object, we measure the distance between this object and all the centroids and assign it to the class with the nearest centroid. No, k-means is what we will see in clustering. They actually share a lot of things, and you can say that k-means is an unsupervised version of Rocchio. So they actually share the same. You will see it in today's lecture. So it's not exactly the same, because k-means starts from unsupervised or doesn't have labeled instances to start with. But you'll see that it's actually, you can see at Rocchio as part of k-means in a sense. So Rocchio is a linear classifier, meaning that it works with linearly separable data points, and it makes some assumptions about the distribution of the points in the space. So they have to be of spherical shape and roughly the same size, etc. And then we looked at k nearest neighbor, KNN, which is an example of exemplar-based, or it relies on exemplar-based representation, meaning that it doesn't compute anything or any new vector to represent the class. It basically memorizes all the training examples, and whenever we're given a new object to classify, we find the k nearest, or we look up the k nearest neighbor and then assign the majority class to this new object. And this turned out to be a non-linear classifier, meaning that the data points don't need to be linearly separable. And that's what we also, a distinction that we established last week is this linear and nonlinear decision boundaries. Yes, any questions on things from last week? Yeah, all clear. So how can we test the classifier? So that's the first part of the lecture today. So again, when we talk about vector space classification, classification itself amounts to computing the decision boundaries. So basically, when you want to learn a classifier, you want to learn the decision boundary. And the decision boundary will tell you whenever you have a new object, whether this object belongs to class A or B, depending on where it occurs in regard to the decision boundary. And since we can actually draw these decision boundaries in maybe infinite numbers of ways, there are infinite decision boundaries here, right? So you can draw as many decision boundaries as you want. You want a way to, or an objective way to quantify how good a decision boundary is, and hence how good is your classifier, since we say that classification is basically drawing decision boundaries. And very intuitively, you could say that to evaluate the boundary, you will measure the number of correct classification predictions on unseen test items. So you run your classifier on a test data set, and then you basically count how many times it got the answer correctly. But there are actually many ways, as we will see, on how to do this, how to count this number of correct predictions. But before that, and last week we focused more on so-called training set, so basically a set of examples that are labeled, but a test set is usually held out, meaning that it's a set of examples that were manually labeled by experts or people who know what we are working with. So it's a reference point for us, and we use test sets or held out test sets to learn or to measure how good our model is, or how good is it in generalizing on unseen examples. So we train it on examples, and then we want to test it on unseen examples. And this is a very important methodological consideration in general, is that you can't train a classifier on a set and test it on the same set. Do you know why? I mean, what would be the result if we just use the same set for training? And 3 hands, which, yeah, go ahead. Yeah, so exactly. So it would be learning so when you test on the training set, you will get a perfect result because you have seen all the examples before. So if your testing set is the same as training, then you have seen all the examples and you basically get all the answers correctly. And that's not what you want. You want to learn a classifier that actually predicts or correctly predicts new unseen objects. And we also refer to the test set as a gold standard, meaning that when we test a classifier, we want to know the truth. So the classifier does some predictions, and we want to know what's the truth, whether this document is for class A or for class B or class C, etc. So this is what we call gold standard. So it's the reality in a sense. So if we look at this example here, let's assume that this is, just for simplicity, this is a spam filtering classifier. So it gets emails and it decides whether the email is spam or not. So ordinary email or spam. So this is our training set. The examples or the red circles are non-spam emails, and the green triangles are spams. And this is the decision boundary. So it's a linear decision boundary, as you can see here. It doesn't really matter. And one thing to notice here is that we have a majority class. So we have a class that has a higher number of examples than the other one. So the majority class in this case is the non-spam emails. and the minority class is the spam emails. So this is our training set. So now we have ran, say, Rocchio, and we learned that this is the decision boundary. We are given this test set. So this is our test set. And our classifier, by just looking here, you see what emails will be classified as spam and which ones will be classified as non-spam. So just looking at decision boundary, these two will be classified as spam and the rest will be non-spam. But since, as we said, this is a test set, so we know the actual classes of these emails. We know whether they were spams or not. So we can color them here. So the ones in red are actually non-spam, and the ones in green are spam. So you can immediately see now that our classifier has made mistakes here. So there is one non-spam email that was classified as spam because it occurred on above the decision boundary, and there are two spam emails that were not classified as spam because they occurred within the region that our decision boundary classifies as non-spam. So these are now these predictions, in a sense. So the being classified as spam while it's non-spam, it's an ordinary legitimate email, etc. These predictions can be grouped in different groups. So can be grouped in 4 groups. So if you assume that our classifier, when it outputs that the document is spam, it outputs positive. So it says that this is positive spam. Sorry. When it outputs a spam class, it says that this is positive. And when it's non-spam, it says that this is negative. So we can come up with 4 ways to classify or to group our predictions. The first one is the so-called true positive, meaning that our classifier classified an email as spam, and it's actually spam. So it's a true positive. So it returned positive, and it's truly positive, if you want, in this sense. And this is where our classifier gets things right. So it's this example here. But another prediction could be false positive, meaning that our classifier said that this is a positive spam email, but in reality it's not. So it's false positive. It's not positive. So the gold standard says it's negative, but our prediction or our predictor or our classifier classifies it as positive, and this is what we refer to as false positive, or sometimes also called type 1 error. And these 2 examples here are false negatives, meaning that our classifier predicts these are as non-spam or negative, but in reality, in the gold standard, they are actually spam. So this is what we call false negative, or also type 2 error. And the true negative is when our classifier decides that these emails are not spam and they are actually not spam. So predicts negative, and the classifier predicts negative, and the gold standard is negative also. So we can put these types of errors in different ways to come up with measures to quantify or to evaluate our classifier. Are they clear? Do you have any questions? So should be straightforward in a sense. So these are now, here we can look at the the test set is the x's. Our classifier decides whether an item is spam or non-spam, depending on its position in respect to the decision boundary. And here we have the types of the errors on as superscript. So one measure we can use to quantify or to evaluate the performance of our classifier is the accuracy. The accuracy counts the number of correct predictions our classifier made in proportion or in relation to the total number of predictions, meaning that it counts how many true positives we have and true negatives over the total number of predictions. So this would be 0.7 or 70%. So 70% of the time, our classifier returned a correct prediction. Yeah. And all the predictions, meaning that it's the number of x's basically here. So we have 10 x's. We made 10 predictions. 7 out of them were actually correct, but correct in the sense whether they were non-spam or spam. This looks very promising. So we have a 70% accuracy. So you might say that this is really good, but the goodness or the the accuracy should be measured in according to sort of some reference point. So how do we say 70% is good enough or bad? We can't just say it's good by looking at the number. We have to have a reference point, a baseline, sometimes referred to say, okay, 70% on this task is actually good. And one reference point or one baseline could be a dummy classifier where everything is classified as non-spam. So we know that this is unbalanced. There is an unbalanced distribution of the data here. The majority class is non-spam, right? So say that we have this dummy classifier where whenever we get an email, we just say that this is not spam. In practice, this will actually give us 70% as well. So if you look at the errors we have, if we put everything as non-spam, we will lose one true positive, but we'll gain one false positive. So overall, we will have also 70% accuracy of this dummy classifier. So this is actually not good. So looking at accuracy when you have a unbalanced distribution of the points in your classes will not give you a sort of a reliable measure. So in such cases where we have unbalanced distribution of the classes, we turn to two measures, which are precision and recall. So and precision, we try to count how many correct predictions we made in the positive class. So we had true positive and false positive, and we want to see how many out of these are actually true, or so were true positive. So this will be concerning this part here. Or so looking at, so I have the numbers, I think. Yeah. So we made one true positive prediction and one false positive prediction as well. So when we divide these, we will have 0.5, which means that now we are looking at less promising classifier. And the recall is how many of the spam, actually spam, so in gold standard spam emails we managed to identify. So that's how we define recall. So it's in this case, it's the true positives divided by the true positives plus the false negatives. So things that we thought were negative, but they are actually false negatives. So then we end up with 0.33. So now we see that it's, yeah. Yeah, so how many of the positive, actually positive in gold standard we were able to identify. So we assigned positive class to. So these two measures are normally used in this setup where you have these two different unbalanced classes, and there is normally a trade-off between a precision and recall. So can anyone guess how we can actually get a 100% recall? So how can we identify all positive examples disregarding the precision? So say that you don't care about precision. Yeah. Uh, and how would you have so if you don't have any false negatives, what does that mean? Correct? No? If you say everything is spam, yes, exactly. So everything is positive, and that's, I guess, what you wanted to say as well. So when you say everything is spam, so you're guaranteed to actually identify all the spam emails, but that also means that you lost a lot on your precision. So many non-spam emails were classified as spam. But this is here comes the trade-off. So where in some cases you are actually interested in having a high recall, even though if that meant that your precision would be lower. So consider a case where you have a classifier helping a doctor diagnose some disease, and you want to be 100% sure, or as sure as you can, that you actually cover all the positive cases, even if that meant that you actually include false positives in your classification, because it's getting this wrong would mean that there is a serious risk on that your classifier will harm a human being. Whereas in cases where you have like a search engine, you're not interested in getting all the relevant documents on the internet. You're interested in precision. You want to have a classifier that's as precise as possible, even though this could mean that recall is lower. So this sort of fine-tuning precision and recall depend on your application. And these two measures are usually combined together in something called F-score. So you could get a measure that actually combines both precision and recall at the same time. So this is, yeah, I think this is just an overview of what we just said. Yeah, so you have that then here. I think there's nothing new here. Yeah. So these measures concern only positive and negative classes, right? So there are only two classes here. We're looking at the classifier that works with two classes. But in real life, we would have classifiers that actually predict work on multi-class work. So document classification, you have 10 classes, and how do you compute then or how do you evaluate a classifier that works with more than just two classes? And here we turn to something called micro or macro averaging and micro averaging. So in macro averaging, what we do is we for each class, so say we have 10 classes, for each of these classes we compute the precision and recall of the classifier, and then we have an overall average, a global average of these. So in this case, macro averaging will be, as written here, will be influenced by small classes, meaning that all classes will contribute equally to the average. So if you have a classification problem where your test set has one instance of class A and then 10,000 instances of class B and some instances of class C, you don't take into consideration how many instances were in their classes, because you go into each class, you compute precision and recall, and then you compute an overall average. So you're blind to how many instances were in these classes, and this would be then of course biased toward not biased, but it would be influenced by the smaller classes more than the larger ones. No, you don't. Yeah. No, you don't weight them, and you don't weight them based on the size of the class. So your classifier predicts and has 4 or 5 classes to predict in, and you just look at them at the same. They're all similar. So to overcome this, you could, but this would introduce a different problem. You can use micro averaging. So micro averaging is different from macro averaging, is that we don't compute precision and recall per class, but what we do is we compute true positives, false positives, or we count true positives, false positives, and false negatives across all classes. So and use these numbers to compute the global precision and recall. And the first one we do this per class. Here we do it for all the instances that we try to test on. This micro average will introduce or will be influenced by large classes this time. So remember we had class A with 10 instances, and then class B with 10,000. Now this 10,000 will actually be influential because we look at the instances themselves and count true positives and true negatives. And so normally what's done is that you actually report both. So if you're writing or evaluating your classifier, multi-class classifier, you would end up reporting macro average and micro average. And of course, what I'm saying here, of course, is all based on the fact that in real life, most of the time, classes will be unbalanced. And that's why we always have this small and large concern, is that we have smaller classes and larger classes, majority and minority. So that was all for classifier evaluation. Any questions? What's the point? These can... Because you can't use these measures immediately with multi-class classifiers. So you need a way to combine precision and recall. If you have these measures work with not two class classifiers, meaning that positive and negative. So spam, non-spam. But when you have a document classification with different classes, politics, economics, etc., then you can't use these. What's a true positive and what's a true negative in this case? There is it's per class. It's done per class. So yeah. Whether your program works as expected. Yeah, that's the overall goal. Yes, is that to see how good is your classifier. But in spam or non-spam setup, these are basically it's so there is no point of using micro and macro averaging because you can get everything you need from here, and it's basically actually computing true positive and false positive and false negatives is done immediately in that case. Any other questions? Okay. Then we can move to clustering, which is the second part of our lecture today. So a cluster is defined, or the noun cluster is a group of similar things or people positioned or occurring closely together. So that's how we define the word cluster in English. And clustering is a set of clusters. So when we say a good clustering is a set of good clusters, just establishing some terminology here. And this whole concept of grouping things together and putting them in clusters based on their similarity in behavior or attributes or feature, that goes back to the 30s and 40s in fields like anthropology and psychology, where people wanted to actually build taxonomies of things based on observations, so empirically based typologies of cultures and individuals. So you don't want to start top down. You sit down and say that there is 10 different classes of cultures. No, I want to look at what cultures we have and build up a typology of this or a taxonomy of this. This is just to general information about clustering. And a clustering algorithm then would actually try to group objects based on a set of features that describe these objects. So the input to a clustering algorithm would be a group of things, or or not a group, sorry, it would be a set of things or objects, and the output would be clusters. So similar or groups of similar objects. So we'll go into more details and more specific definitions of what's clustering. But in general, last week we also looked at this that there are two categorization tasks in machine learning. So there is classification, which is what we just described. Again, it's supervised learning, meaning that we require a set of training examples that are labeled, and we use these to train a classifier and learn how to predict the classes of new objects. Clustering is an instance of unsupervised learning. So we learn from unlabeled data. So our input is basically just a set of examples, or a set of objects, not examples, that are unlabeled. And our task is to automatically group them, or group the objects, the similar objects together. And so in reality, we don't have any predefined classes, so we just have data points, and that's all what we have. And we provide the algorithm with the data points, similarity measure, and the number of clusters that we wanted to return. So a similarity measure is something like Euclidean distance and cosine similarity, etc. And this is what the clustering algorithm will use to find similar objects and put them together in groups. And the overall general objective is to given a data set of points, we want to partition these points into subsets where the members of the same subsets are as similar as possible. So we want to achieve a homogeneous set of objects, but the objects from different subsets are as dissimilar as possible. So we want the objects within the same subset to be homogeneous, but when we go across different sets, we want the objects to be heterogeneous. That's the overall objective of the task. Yeah. You mean like background knowledge to? Yeah. So if I understand your question correctly, is that the input is still unlabeled objects, but now you're saying that this object and that are more important than other objects, and that would be still clustering. But then we would say, if because you don't have any sense of what are the classes within the input data set. But then we would say that this is a background knowledge for the classifier, and as we will see later, this would be actually helpful if you think that if you give the clustering model a sense of which points are more important and therefore more representative maybe, then the task of clustering would be easier. And we will see that later. We'll come to this point and where we need to start from somewhere. Yeah. So what are the applications of some concrete examples of clustering in real life. So we can think of clustering as a way for understanding or knowledge acquisition. So you can think of something like if you, for example, biologists, they have a huge amount of genetic information, and they don't have predefined classes of the different genes. They don't know where to start. So they need to explore this data somehow. So we use clustering to group the different genes according to their behavior, to their functionality, and then use that maybe for them to start with different classes. So, and this is clustering. It would be very common in these fields where you have huge amounts of data, but you have no sense of the structure of the data itself. So you don't know what are the classes, what to expect there, what are the patterns. So this is how we can use clustering for to help us acquire knowledge or to understand our data as a very first step. So this would be the first step, and then from there on, at least you have some groupings, and you can decide whether these groupings or these clusters make sense or not. Another very common use of clustering is within IR, within information retrieval. Sometimes referred to as these sets of examples are sometimes referred to as clustering for utility. So you use them to do some task, and for example, you can speed up the search, meaning that instead of comparing with individual documents, you look up a cluster of documents. So given a query, you look up the relevant cluster, and then when you have these relevant clusters, you can do more fine-grained ranking. So then it would be much faster. Another way is how we present the search results. So today, when you search, you get the list of ranked documents. But these documents could belong to or could be describing the same things, so you could actually present a cluster of documents as in the returned list of relevant documents in a search engine. I think there were a couple of search engines doing this. And one important application actually that we haven't talked a lot about dimensionality reduction. Maybe we haven't mentioned this at all. So one important application is dimensionality reduction or class-based features. So when we worked with vector space models and assignment 2A, each feature within the bag of word context introduced, or each word in our case introduced a new feature, a new dimension, right? So each unique one, each word type introduced a new dimension. And you were using a relatively small corpus. In reality, you would be working with 3 billion words, maybe more, and then the number of dimensions would immediately grow to hundreds of thousands, so 300,000 dimensions. So this is very difficult to work with, and it is in terms of efficiency, in terms of memory. So we employ methods that are normally called dimensionality reduction. So we try to reduce the number of dimensions within our vector space. And clustering could be one of these methods. So you could use clustering to, so again, if you go back to the assignment or the assignment you worked on, so first of all, you try to cluster the words within the Brown corpus or the part of the Brown corpus you had. So you cluster these words into different groups. So things like egg and cheese and etc. So edible material would be grouped into one cluster. Drinkable material would be grouped into one cluster. So you create clusters of things or of concepts within for your Brown corpus, and then you build the vector space model or the occurrence matrix as normal. But this time, your features would not be the individual words themselves, but whenever you see a word that belongs to a cluster, your feature would be the cluster itself. So words like cheese, egg, and chicken, etc., would be within the same cluster, hopefully, if our clustering model or algorithm works, which means that they wouldn't introduce a new dimension. Each of them wouldn't introduce a separate new dimension, but they would be all on the same dimension, which belongs to that cluster. And this is a way where you can actually reduce dimensionality, but at the same time keep the knowledge, preserve the knowledge that you have acquired from the context. And that's why we call it class-based or cluster-based features. There are many other, so another example is the news aggregation. So again, you don't have labeled examples of pieces of news, so you want to put them in different clusters, etc. So this basically all kind of sort of predict or trying to learn patterns within data, be it social network profiles or genetic information. All of this you don't have a clear vision of, or you don't know what to expect, so you apply clustering for this on this. So in general, we distinguish, very broadly speaking, we distinguish between two types of clustering. So in flat clustering, we try to decompose the data into a set of clusters. So we're given a set of data points, and each of these data points would be belonging to one cluster without any structure, just flat. And hierarchical clustering would create a structure. So meaning that there will be a tree of clusters. So clusters would be nested, and an object could belong to cluster A, and then cluster A would actually be a member of some other cluster. So it's basically a tree. We will be focusing on flat clustering. This last year we had hierarchical clustering, but this is not part of the curriculum for this year. So in flat clustering, we also could think of different ways on how we can also sort of group the different models. So we know what's hard clustering and soft clustering, because we know what's hard membership in classification and what's soft membership. Again, it's either or. But we can also introduce something called partitional clustering. It's basically hard clustering, meaning that an object is a member of a cluster or not, but it also requires that the object belongs to only one cluster at a time. So it can't belong to more than one cluster. In hard clustering, we allowed this. So we said an object could belong to different clusters, but or different classes. And for each of them, the membership is hard. So it's either or, but it still can be member of different groups or different classes. And partitional clustering, this is not the case. It's only in one cluster. And this is what we will be. So whenever we say clustering from now on, we are referring to partitional clustering. So, and this is what we will be covering, unless we say otherwise. Okay, so we take a break now, 15 minutes, and we come back. So before the break, we introduced flat clustering, and we said that we're going to focus on the partitional clustering part of this. So we have, so in information retrieval, there is something called the cluster hypothesis, and it's actually in machine learning in general, which states that documents in the same cluster behave similarly, this similarity with, okay, that should be behave similar with respect to relevance to information need, meaning that objects within the same group or the same cluster are somehow more similar to each other than objects in other groups. So this is just a hypothesis we will make. So in order for clustering to work, and this whole assumption that objects within the same region, within the same cluster are similar, for this is a hypothesis that we build on, or sort of borrow from the contiguity hypothesis in classification. If you remember that objects belonging to the same class happen to be in the same region within our space, and this is more or less the same. So these clusters that are within the same region, they actually behave similarly or share some attributes. And so to define clustering in a more, or flat clustering in a more formal way, we are given a set of objects O, so O1 to On, and we want to construct a set of clusters C from C1 to Ck, so K clusters, where each object OI is assigned to a cluster Cj. And typically, when we work with clustering algorithms, we would have to provide two things. The first is the cardinality, K, so the number of clusters. Remember, we don't know anything about the data, and so we don't know how many clusters. So we have to provide to the clustering algorithm some number. We will see later on how we can, or if we can actually guess what this number is, but this should be an input to the clustering algorithm. The number of clusters, or the so-called cardinality, and a similarity function. So similarity function S, which could be Euclidean distance or anything else that help us measure the similarity between objects. And even more formally, you can define clustering as finding an assignment or a function gamma that actually maps points from O, the set of input objects, to C, the set of clusters. All of so that in a way, or so this mapping or this function should also optimize some objective function. So in optimization or optimization problems, we always have an objective function that we want to either minimize or maximize, and we can define clustering as an optimization problem where we look for a function that does the mapping from O to C, and also optimizes this objective function, which we will return to. What could be this objective function? But generally speaking, this objective function would mean is that we want to have high intra-cluster similarity, again homogeneity within the cluster itself, and low inter-cluster similarity. So the objects belonging to different clusters should be dissimilar. So defining this clustering problem as an optimization problem means that we can actually also approach this problem as a search problem. So remember, the clustering is basically partitioning the set of points into different clusters. And this could be done in a finite number. So this means that we can actually follow a naive brute force approach where we enumerate all possible clusterings and measure the objective function. So this all possible gammas, all possible mappings from O to C, and we compute the objective function for all of these, and when all of the possible mappings or the partitionings, and pick the one with the best value. In our case, could be the minimum or the maximum, so the optimal value. So this is something that in theory could be done, but in practice it can't be done. So in practice, this means that we have exponentially many number of, or many possible partitionings. So you can't just, if you have 20 or 20,000 or 100,000 objects, and you want to cluster them in 100 clusters, that can't be done so efficiently, and you could think of higher numbers. So this is the brute force way cannot work. But we can, or in general, clustering algorithms would approximate this solution by starting somewhere, a random place, random partitioning, and then iteratively try to improve this solution. So we don't know how to look at the data. So we start randomly. We say that these points belong to that group and these points belong to that cluster, and iteratively keep on improving the clustering until we meet a stopping criterion, or until the algorithm converges. So k-means is an example of clustering algorithms, and it's as asked before. It's actually very relevant to Rocchio. It's seen as an unsupervised variant of the Rocchio classifier. And again, our goal is to partition we have n observed objects as input, and we also input that we want these n observed objects to be clustered in k clusters. So k clusters C, referred to as C, so that each point xj within of our observed objects belong to one cluster Ci, and that cluster has the nearest centroid to this point. So this is how we divide our points. So again, we're given a set of input n objects to cluster, and we want to cluster them in k clusters, referred to as big C, so that each of these points is assigned to one cluster, and that cluster has the closest centroid to this point. And the distance, so the closeness or the closest centroid or nearest centroid, is measured normally using Euclidean distance. And this would be our similarity function for the algorithm. And now back to this optimization problem and how we can actually recast the clustering problem as an optimization problem. So we can define an optimization problem here by providing an objective function to the clustering algorithm. And this objective function in our case is within cluster sum of squares. And what this objective function does, or what this WCSS means, is that we sum over all the clusters the squared difference of the distance between each point within the cluster and the centroid. So for all clusters, for all clusters Ci and C, and for all points within or objects within Ci, we compute the squared distance between xj and the centroid of that cluster. And the squared, because we don't want to negative to cancel out the positive. That's why we look at the squared. And this is more or less equivalent to minimizing the average squared distance between objects and their cluster centroids. So again, we're looking at different clusters that has different objects. And if we remember in Rocchio, we had a centroid representing the class, right? And this objective function, what it tries to do is to make the centroid as representative as possible of the cluster it's representing. And this is still not the algorithm itself. We're still trying to formalize the definition of k-means. So the algorithm itself, again, we have this goal. Is what we do is we first randomly select k centroid seeds, so-called centroid seeds. Again, we don't have any information about the data, so we have to start somewhere, and that somewhere is random. So we say that, okay, we want k clusters, so we want k centroids. We pick k random centroids, and based on these, so the first iteration, we have k centroids. So what we do is we go through all the objects in our input data and assign each object to the cluster with the nearest centroid, and then recompute the centroids again. So we'll see an illustration of this. And then iterate, keep on doing this, keep on reassigning the objects and then recomputing the centroids until we meet some stopping criterion, or so it's iterative reassignment of memberships and recomputation of centroids until the configuration stabilizes or until the algorithm converges. So this example is from the IR book. So say that this is our input data. So these are the points that we want to cluster. We randomly, and our k is 2, so we want to have 2 clusters. Well, that's our goal now. We randomly pick 2 points, so the ones that are marked with X's here. So this is the first step, initialization. This we do once. Then we measure or we assign the different points here to the nearest centroids, because now we take these two as centroids of our clusters. So we do this assignment and we recompute the centroid. So after assigning, now we have actual objects belonging to the cluster, and so we can compute its actual centroid. So this was, remember, this was just random value. So we just a random object within the space. And when we recompute the centroids, the nearest centroid now to these documents is different, or to these objects is different. So we have to do reassignment. So we go back to this step and back here. So we continue on doing this until we reach some point as defined by a stopping criterion, and our clustering would look like this. So this is after iteration number 9. Yeah. Yeah. So the similarity function would be an important factor in how your cluster will look like. So that's an input you choose. And what on this graph here, you can actually see the movement of the centroid. So we started here with the first centroid, and then we see that it actually moved to this point. It's not very clear. It's not a high resolution, but you can see. So this arrow here says that the centroid moved actually quite a lot in the first iteration, and then the more iterations we do, the smaller the steps are, because the algorithm is actually moving towards convergence. So it's going to stop at some point. Is this clear? I mean, I know it's sometimes not very intuitive to get this. Yeah. No. Yeah. Yeah, on the initial. So if you don't, there is no guarantee that you actually can reproduce the same results, and this is one of the disadvantages of k-means. It's completely dependent on the random choice you make in the beginning. And here, so yeah, next time you pick two different points, you will have different clusters. Yeah, go ahead. Not necessarily. You can also pick a point that's actually not an actual object. So we will see that. So you can either pick a point that's an actual object, a random point, or you can also just pick a point on the space and say this is going to be my first starting point. When we'll see different ways of picking the seeds. These are called seeds. Yeah. That's also something we'll look at just in a few minutes. But this is sort of the overall way or scheme of the algorithm. This is how it works. So we start randomly somewhere. We assign documents to the centroids, seed centroids. We recompute the centroid and then reassign documents and so on and so forth. Because you don't have any information. That's the problem. You don't have any clue what's in this data, what's the structure, and you can try the brute force way, which is try all partitionings, but that's not feasible. You can't do that actually. So you have to start somewhere, and that somewhere is actually random, and but here actually commenting on what you said before, or the question you asked before, is that if we know that some points are more important than others, this could actually help you in identifying where the starting points of the centroids, the seed centroids, would be. And this would be sometimes referred to as clustering with background information knowledge. So some knowledge about the structure, but not so much. So This is, sorry. Oh, the same. Sorry. Yeah. 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 You compute the so when you assigned points to the to clusters, you can now compute their average, right? As we did with Rocchio, and that would be your new centroid. But since the centroid has now moved, it was there, so it would be closer to some other objects, which would introduce a new cluster, which means a new centroid, and so on. Yeah. Is there any other questions? Okay, so some properties of k-means is first of all, its complexity is actually linear in terms of the number of objects and the clusters. This within cluster sum of squares, this objective function is actually monotonically decreasing for each iteration, which means that actually we are guaranteed. So the algorithm is guaranteed to converge. So it's monotonically decreasing means that it's at some point it's going to stop. But it's not guaranteed that it will actually find a so-called global minimum. So in optimization problems in general, we talk about things like global minimum and local minimum, meaning that, so say that you started your random seeds where, so this is where you start and you move in this direction, and so you start your search here and you move in this direction, and then you end up seeing this minimum. Local, it's local because if you move to the right, the value will be increasing, and if you move to the left, the value would be also increasing. So it's local minimum in this part of the graph, but not overall. So this random starting point means that at some point we will get stuck in a local minimum, and we will never see this global minimum. And there is no way you can actually solve this. Some people say that you can, for k that's less than 10, you can actually run multiple random initializations. So you run the same clustering algorithm for say 100 or 1000 times, and each time you start with a completely random new initialization, and maybe you're bound then to find this global minimum. But there's no guarantee you can actually find it. This is a potential solution, but not necessarily is going to work. Yeah. The best case is to find a global minimum, of course, the best clustering, but there is no guarantee that that's going to happen because of the random nature of your starting point. And this is where, yeah, so now we need to find, or sort of, how can we actually pick these k random points or starting or seeds. So as said before, we initialize the algorithm by choosing random seeds that we use to compute the first iteration and compute the centroids. And there are different ways to or heuristics to select seeds. So you could pick k random objects from the collection. So that could be one way to do it. Another way would be picking k random points in the space. So you could just pick random points, not necessarily corresponding to objects within your input. You could also, so if you have k clusters, you could for each k pick m points and then compute the centroids of these, or the centroid of each set of m points as one of the k's. So k sets of m random points, and compute a centroid for each set, and that would be your seeds. You can also compute you can run a completely different clustering algorithm and use the output of that as an input to k-means. That's also a possible way of doing it. I mean, like for example in hierarchical clustering, a subset of the data can be used to as an initialization for k-means. Yes, and as said before, these initial seeds will have large impact on the resulting clusters. So getting stuck in local minimum or similar cases. And outliers, we talked about this before in classification, they are problematic whether in classification or clustering. These are noisy points that you have a cluster of points, but then you have a point that's very, very far away from the group of points you're looking at. And this would actually influence how you compute the centroid. So to be pulling the centroid towards that. And this can be very problematic. One way to work with outliers is to assign them their own clusters. That some people do that. So that you don't pull the centroid of a condensed cluster of points to somewhere that's actually not correct in a sense. And so how do we make sure that the algorithm stops? So we need some stopping criterion. So one way to do it is to actually set a number of iterations predefined. Say after 20,000 iterations, just stop. Just keep on counting and you stop. A more sorry. A more sort of informed way of for a stopping criterion is you look at the centroid and you see if the centroid hasn't changed its position from or its values from one iteration to the other, then you stop. So there is no change in the centroid or the cluster itself. You can also define a threshold. So if the centroid changes within or within a value that's less than the predefined threshold, then you can also stop. You can say that there is no remarkable or significant changes in the clusters, so we can just stop the algorithm. And there are some relative or close variations of k-means. So k-medoids is one example of this. So if you remember, medoids were central points within the class that were the most representative. So unlike unlike centroids, medoids are actual points within a class that are central to this class in some sense. So we can use medoids instead of using centroids in k-means itself. And then it would be basically the same process, but again, we don't compute centroids. We look for medoids. Basically, we look for within our cluster for points that are most representative of the cluster itself. And most representative mean as the least average point or pairwise dissimilarity. And we can also work with fuzzy k-means. C-means. I don't know why is that here. Which is basically the same as k-means, but then we have a membership value. So soft membership, saying that an object is a member of a class for a value between 0 and 1. And the membership is also would be a function of and the distance to the centroid. So this is one thing that we can take into consideration, and then also can factor in computing the within class sum of squares and the centroid itself. So that's just also small variation that we can add to the algorithm. So what are the pros and cons of flat clustering? So as you can see, it's rather simple. So it's not that difficult to understand or implement. And it's efficient since it's linear and the time of linear in time with regard to the number of objects, but it has several disadvantages. So one is this dependence on the random seeds, which means that our clustering algorithm is actually non-deterministic, or we don't know, or where there is no guarantee that if we run the same algorithm several times on the same data set with the same similarity object, when all parameters are the same, there's no guarantee that we get the same results because of the randomness in the beginning. And the number of clusters, k, must be specified beforehand, and we don't know actually what's the best number of k's for a clustering, so we have a problem. So we have a data set of Facebook profiles, but we don't know how many clusters there are within this within this data set. So we have to actually try and it's a trial and error. So we start with K2 and 3 and 4 and see how many meaningful clusters we get. But this is a disadvantage of the algorithm. It's not a disadvantage of the concept. I mean of k-means itself as in is more a disadvantage of clustering in general as a concept is you don't know what you are looking for. In more sophisticated but less efficient methods like hierarchical clustering, we get better overview of the clusters. And flat clustering, it's flat, so you don't have any structure. So it's most of the time the quality of the cluster is inferior to those produced by more sophisticated, but of course much more or much less efficient. And again, we don't have access to, this is basically the same. We don't have access to more so information as much as in the structured clustering. So just to make these comparisons with the different algorithms we looked at in this lecture and last lecture. So we looked at Rocchio, which is the nearest centroid classification, also referred to Rocchio and IR, general nearest centroid classification, key nearest neighbor, and k-means. And you can see now, as you know both algorithms, you know k-means and you know Rocchio, that actually k-means is performing Rocchio in each iteration, right? So because in each iteration we have centroids, and we reassign documents to the closest centroid, and that's what Rocchio does. But Rocchio starts from a set of training examples, labeled examples, and we know the classes and we know everything, so the centroids are fixed. So basically in each iteration we have Rocchio. Also, you can think of Rocchio as one nearest neighbor classifier with respect to the centroids. So when you have one NN, Rocchio could be also a 1 NN classifier. So this time we don't look at the members. Of course, we're looking at the centroids, but still it's one nearest neighbor. But this might sound a little bit weird to some of you, I guess, because we said that K and N is actually nonlinear, and Rocchio is linear. But now what we're saying is a Rocchio is actually an instance of this nonlinear nearest neighbor. So what's the catch here? Yeah. So it's when you look at the sort of how we draw the this Voronoi diagram last week, when we look at one instance, only one instance, so locally its decision boundaries are linear. But when we look at more than one instance, then it becomes nonlinear. And if you could understand this more easily when you look at these were the decision boundaries we draw from in Rocchio, right? So we said that this line here is on equal distance between the centroid of UK and the centroid of Kenya. So this means that all points within this region is actually as closer to Kenya than any other points. So this here is actually a Voronoi tessellation. So 1 NN or locally for one instance you have linear boundaries, but when you combine them together, then it becomes a nonlinear decision boundary. I mentioned last time some comments on assignment 2B very quickly, that you are going to build on 2A to create to represent classes, and you're going to implement Rocchio. I just want to add one thing, is that we ask you to compute this proximity matrix, which is an m by m matrix, which is going to be 122 by 122. And basically what it tells you is that when you look at a cell ij, it tells you the similarity between word I and word j. One important consideration when you implement this is that this matrix is symmetric, meaning that the similarity of xy equals the similarity of yx, right? So this is something you should take into consideration, and the way you represent it. So ideally you should not be representing redundant data, meaning that your matrix cannot be representing xy and yx, similarity of xy and similarity of yx. So this is just something to keep in mind. And the rest you can just read from the lecture notes. I actually have a quiz, so I think we have time for a quiz. And there are no points for this quiz, it's just for fun. So this is Kahoot, so you all have either mobile phones or tablets or computers, and just I have to stop the recording here.